Assalamu alaikum. So previously we have been studying about the passive filters, and within the passive filters we covered the low pass filters and the high pass filters and their characteristics, especially their frequency response for the low pass filters and the high pass filters. And then we also covered some information about the second order filters. So basically second order filters के बारे में हमने बोला था कि second order filters are required when we need some faster response for our filters. So basically, as we told, that for our first order filters we have a slope of around minus 20 dB per decade, and decade we showed that decade means the 10 times of the frequency when we are changing it by the 10 times of the frequency. So we are actually not happy with that slower response, and we want some faster response for our filters. So that's why we move towards the higher order filters. And then we told that about the second order filters that are actually achieved when we are cascading or joining or grouping together two first order filters, and then at the end we will be getting second order filters. So in this way, by cascading, we can achieve higher order filters. So what we will be getting, so that for example, we were getting around negative 20 dB per decade of the slope for our first order filter, and then for our second order filter we will be getting negative 40 dB per decade, and similarly for third order negative 60 dB per decade of the slope or the roll off, and then for the fourth order filter we will be getting around negative 80 dB per decade. So we can actually achieve a higher slope or the faster response by increasing the order of our filters. But that was the case for the passive filters. And then we also discussed that there are basically some downside about the increasing order of the filters. And the first thing that we studied was that that the gain and accuracy of our higher order filters actually decline when we are increasing their order. And the frequency gain at the critical frequency or the corner frequency is actually around equal to the 1 divided by under root 2 and whole raised to power to the n, and n is representing the order of the filter. So हमने ये चेक किया था कि हमारा जो कॉर्नर फ्रीक्वेंसी का पॉइंट है, सो वी टोल्ड दैट इज इक्वल टू द नेगेटिव 3 dB के जब हमारे मैग्नीट्यूड ऑफ द आउटपुट वोल्टेज या आउटपुट सिग्नल और द गेन ऑफ आवर सिग्नल जो है वो दैट स्टार्ट्स डिक्रीजिंग बाय द नेगेटिव 3 dB, then that point is called the critical frequency or the corner frequency in case of our low pass filters. So this negative 3 dB is actually coming from this whole 1 by under root 2. So basically 1 divided by under root 2, if you open it, that comes equal to the 0.707, and when you want to convert it into the dB scale, then the formula is 20 log of this gain value 0.707, and that actually comes around log of 0.707, that comes around negative of 0.15, and when that is multiplied by the 20, then we get negative 3 dB. So that's where it's coming from, the corner frequency. So, and we told that that is actually over here when we are drawing their body plot. So we have a frequency over here, and then we have a gain in dB around the y-axis, and then we call that is almost constant, but at the critical frequency that comes around 0 and minus 3 dB, and that one was the minus 20 dB. So that was the whole story about the corner frequency कि जब हमारा gain of our input signal that decreases by the negative 3 dB for the low pass filters, and then we call that particular point as the corner frequency or the cutoff frequency. So then we discussed that when this slope was actually negative 20 dB per decade, and then we told that if we want to achieve some higher slope, let's suppose by let me draw another one. So if we want to achieve some higher slope, so we actually increase the order of our filter. So we will be getting around negative 40 dB for the second order, and this was the original one at the FC, and we were having around negative 20 dB per decade for the first order filter. So then we also discussed that के previous lecture के अंदर कि हमारा जो critical frequency का point है that is also changing, and the other issue is about the pass band range that is also shifting. So अगर हमारे पास first order के केस में यहाँ पर थी, then हमारा point जो है for the second order is actually coming over there. So इसका pass band जिसको ये allow कर रहा था that is also changing. So these are some of the downsides for our higher order filters. कि उनके केस के अंदर क्या हो रहा होता है कि ये दो चीज़ें आ रही होती हैं कि एक तो उनका जो गेन है that is also declining when we are increasing the order, and the second thing is कि उनकी accuracy भी कम हो रही है because the pass band that was earlier in the case of our first order filter, now that is not the same when we have increased the order of our filter. So for example जब हमारे पास second order filter आ जाएगा तो उसके लिए हमारे पास जो gain होगा at the corner frequency that would be around that was 0.707 for the first order. For the second order gain at FC corner frequency, that will be actually 0.707 multiplied by 0.707, and that will be around 0.5 V in of the input voltage, and or that would be around negative 6 dB. So similarly if we are increasing another order for the third order, तो हमारे पास जो gain होगा at the corner frequency that will be around 0.707 multiplied by 3 times of the 0.707, so that will be around 0.353 of the input voltage, or that will be the negative 9 dB. So as we are increasing the order of our filter, so our gain that we are achieving at the corner frequency is also getting reduced. तो हमने बोला था कि जो हमारे पास corner frequency है for the first order filter, that is achieved when our gain actually gets reduced by negative 3 dB, yeah, that is actually equal to the 0.707 of the input voltage, then that point is called the corner frequency. But when we are increasing the order of our filter for the second order, we will be achieving a gain of 0.5 or half of our input voltage or negative 6 dB, and for the third order filter it will be further reduced by 0.353 of the input voltage or negative 9 dB. So that is the मेजर डाउन साइड ऑफ द हायर ऑर्डर फिल्टर्स कि उनके ऊपर गेन भी हमारे पास कम आ रहा होता है. सो टू टैकल दीज प्रॉब्लम्स we move towards the active filters, and we know that for the active filters these are actually made from the active components, which we told that they are actually getting their power supply from an external source. For example, in case of our transistors and our op amps. So most frequently or the most commonly our operational amplifier are actually used as the active filters. So they have their own advantages. So the first one is we can achieve voltage amplification from them, or an extra gain or the amplified version of our input signal. And then the second thing is that we studied while we covered the characteristics of the operational amplifier, and then we told that operational amplifier actually have a very high input impedance and very low output impedance. So those can be used as a buffer. और इट मीन्स कि जब हमने लोड के साथ कनेक्ट करना हो and our load is also varying, so our operational amplifier is basically independent of whatever the load is connected at its other end, because its input impedance is very high. So that's why on the source side there is very little effect on our input signal or the source signal. So now let's move towards the low pass active filters. So for the low pass active filter, the thing is कि हमारे पास एक operational amplifier होगा that is acting as the active device, and then we will be having the same passive RC network that was in case of our low pass. That is the series circuit of the resistor and the capacitor, and then we are also applying an input voltage signal at the input terminal or the non-inverting terminal of our operational amplifier. So this is signal is applied at the non-inverting end, and then we have just directly connected our inverting terminal with the output. So we can say that this is basically a buffer, और जिसका सेकेंड नेम था वोल्टेज फॉलोअर. Op amp with RC low pass network at its non-inverting terminal. क्योंकि ये बफर है, so whatever the voltage that will be coming at its positive terminal, our negative terminal will also try to follow it, as we have covered in the operational amplifier chapter. So our V positive will actually become equal to the whatever is the input into the reactance of our capacitor, that is output, and divided by the sum of the impedance of the resistance and the capacitor, and that comes around R square plus XC square. And then again, because हमने feedback के अंदर कुछ भी नहीं लगा हुआ, so feedback is directly connected with the inverting terminal. So whatever is coming at the V positive terminal, that will be also coming at the negative terminal, and that will be directly connected with the V output. So we can say that our output voltage will be also equal to the voltage being received at the non-inverting terminal, and that is equal to the same thing that we have just derived, and that is equal to the V in multiplied by XC divided by r square plus xc square. And then the formula for the corner frequency is the same as we derived or looked for the passive filters, that is equal to the 1 over 2 pi RC. So we can simply calculate the corner frequency for a particular low pass active filter. Then the other thing, instead of using the buffer, then we can also have some other operational amplifier which has something in its feedback, and we are denoting it with the RF, that is within the feedback resistor, feedback circuit. And then we have this RG just for changing the names. And then again we have the RC network denoted by the R1C1 at its positive terminal, and we are also applying an input voltage at this terminal. So for this particular circuit, now this is not acting as a buffer, but instead we will be getting a voltage gain, that is the ratio of the V output divided by the V in, and we have derived this relation that was equal to the 1 plus R2 divided by R1, but over here R2 is replaced by the RF and R1 has been replaced by the RG. So that's why we can now get an amplified version of our input signal, और ये उसका गेन का फार्मूला जो कि हम ऑलरेडी पहले पढ़ चुके हैं. अच्छा, जो इसका दूसरा रिस्पॉन्स आएगा हमारे पास, that is the frequency response, and that one would be the same that we have already covered. और वो क्या होगा लो पास के केस में, that would be simply के लो फ्रीक्वेंसी सिग्नल्स के ऊपर जो है that will be having some constant magnitude, but soon it will be decreasing by, क्योंकि ये फर्स्ट ऑर्डर है, so that would be negative 20 dB per decade. तो अगर ये पॉइंट हमारे पास कॉर्नर फ्रीक्वेंसी था जिसके ऊपर हमारे पास -3 dB आ रहा था, so this is a -20 and this one over here is a 0. So at this point we will be getting almost -20 dB. So that is simply the frequency response of our low pass active filter. That will be same as we have covered in the passive filters, but the only difference would be this gain that we have achieved now by using the operational amplifier. So now let's move towards the सेकेंड ऑर्डर लो पास एक्टिव फिल्टर्स. सो अगेन जैसा कि हमने उसके अंदर पैसिव फिल्टर्स के अंदर पढ़ा था कि दैट वी कैन अचीव द हायर ऑर्डर बाय कैस्केडिंग द फर्स्ट ऑर्डर फिल्टर्स. सो द सिमिलर थिंग वी विल बी डूइंग ओवर हियर कि अगर हमारे पास दैट वन वाज द ऑपरेशनल एम्पलीफायर एंड देन वी हैड सम one RC network over here and then a second RC network over there and grounded, and we also have one input signal at this terminal. And then again, if we want to achieve some gain at the output, so again we will be getting the same. So इस केस के अंदर भी हमारे पास जो gain है that will remain same, that would be equal to the 1 plus RF divided by RG, and then we have the two networks at the input terminal, that is the R1, C1, R2 and C2. तो हमने जिसका फार्मूला पढ़ा था फॉर द कॉर्नर फ्रीक्वेंसी, दैट वुड बी सिंपली इक्वल टू द 1 डिवाइडेड बाय 2 पाई, बट नाउ देयर विल बी R1, C1, R2 and C2, and those will be inside the square root. और फिर हमने ये कहा था कि ये हम क्यों करते हैं, बिकॉज वी वांट अ फास्टर रिस्पॉन्स. फॉर दिस केस वी विल बी गेटिंग, इंस्टेड ऑफ द -20 dB, we will be getting a much faster slope. Let me show it, and that one would be the -40 dB per decade. So that is the 10 times of the FC, and let's suppose our corner frequency occurred over there. So now that was a 0, so this one we can say that is a negative 40 dB that has been achieved after the decade of the corner frequency. So that is the second order. So similarly we can go for the third order and the fourth order as well. So now let's try to see what would happen if we have a particular circuit. So this is some kind of example. So let's suppose that that we have a operational amplifier, and that is also a kind of the buffer. However, we now have an R1 over here and R2 over here, and then a capacitor is also grounded, and over here we are getting an input signal. That one is the R1, R2 and C2, and then we also have one RC network over there, so that is a C1. So this is basically again a second order filter. So the first network is being formed by the R1 and the C1, and the second one is by the R2 and the C2, and we have the values for the R1 and R2 that are equal to the 15 kilo ohms. This one is also 15 kilo ohms, and C1 is equal to 0.015 microfarads, and this one is a 0.0075 microfarad. So from here the condition is that R1 is equal to R2 and C1 is equal to 2 times of the C2. So that's the condition for this, and let's see what would be the corner frequency for this one. So we know that the corner frequency for the second order is 1 divided by 2 pi square root of R1, C1, R2 and C2, and then after inputting the values we will be getting a corner frequency of around 1 kilohertz. So you can just check it later by performing the calculations. I have just performed them. So we can get a corner frequency of the 1 kilohertz for this specific second order filter. So if we want to further change the corner frequency, let's suppose that if we want Fc is equal to 2 kilohertz, then we can simply achieve it by reducing the values of the C1 by halving the value of the capacitor 1, and similarly for the capacitor 2. So if we do that, then we will be able to achieve our 2 kilohertz of the corner frequency. So you can just check them later that whether we are able to achieve it or not. Similarly, we can also achieve it if we double the capacitors, and then we will be able to achieve around 500 hertz of our corner frequency. So there is actually an inverse relationship between the capacitance and the corner frequency. So that was the thing for this particular example. So now let's move towards another example. So that's an example number 2. So now again we have another problem that कि हमारे पास एक operational amplifier है, and that has almost a similar circuit कि इसके जो है positive के ऊपर we are applying an input, and we have two networks, R2 and C2, and then this one is actually directly connected, and then we also have a network over there. So that one is the C1. So this problem says that we have to calculate the capacitors values C1 and C2 for a corner frequency of 3 kilohertz. So that is quite simple. Again, we know that कि हमारे पास जो corner frequency का formula है, that is equal to the 1 divided by 2 pi R1, C1, R2 and C2, and the condition for the given one was that this C1 is actually equal to 2 times of the C2. Alright, so again the same thing that we covered earlier in our example. So but we are not given the values of the capacitors and we have to find them, and we are given the value of the corner frequency. So simply again our R1 and R2 are actually equal to each other, and their given values are 22 kilo ohms, and this one is also 22 kilo ohms. So we can say that R1 is equal to R2, and that is equal to the R, that is equal to the R, that is 22 kilo ohms. And our C1 is actually equal to the 2 times of the C2, so we can just simply put it and solve our equation. So we will be getting around R1 is equal to R2 R square into C1 is equal to the 2 times of the C2, so we will be getting 2 times of the C2 square. So that is the value that we will be getting. So again we can simply write it as 1 divided by 2 pi r into under root of 2 C2 square, and that was equal to the corner frequency. So if we take the square of the both sides, so we will be getting f square of C 1 divided by 4 multiplied by 2 into pi square r square and C2. Square, so that's right, yeah, that's the one that we will be getting by taking the square of the both sides. So if we input the values for everything that we have, that is equal to the 8 into 3.14 square pi value, we have R is equal to 22 kilo ohms, and our C2 we don't know about it, and that is over here, but we know the value of the FC, that is the 3 kilohertz. So we can simply write that C2 square, that can be equal to the 8 into 3.14 square into 22 kilo squares, and FC square is equal to the 3 kilohertz square. So after solving that one, you will be getting around C2 equal to the 0.0017 microfarad. So that will be the value of the C2, and we know that our C1 is actually equal to the 2 times of the C2. So multiplying it with the 0.0017, we will be getting around 0.0034 microfarads for the value of the C1. So again the same thing, that if our C1 is equal to the 2 times of the C2, then we will be getting around corner frequency of the 3 kilohertz for that particular circuit when our R1 is equal to R2 and both have the value of the 22 kilo ohms. So that is the second example for our low pass filter. So now let's move towards the high pass active filters. So just like the low pass active filter, again we will be have our operational amplifier, and then only we have to swap the position of the capacitor and the resistor, and over there we will be having our input voltage, that will be R, and that is actually now a buffer circuit or the voltage follower. So again over here our V positive now will be equal to the V in, but now this time that will be the R in the numerator, but the denominator will be the combined impedance plus XC square, and this one will also be equal to the V output because this is the buffer or the voltage follower circuit, and the frequency response for this one would be the same that we have studied earlier, that for the low frequencies there is nothing, but when we are reaching some particular values then it will be approaching that value, and because that one is first order, that will be a plus 20 dB per decade, and some point over there will be the corner frequency where we are actually achieving around minus 3 dB, and that one is our 0 dB, and this one was a negative 20. So that was the frequency response for our high pass filter. So similarly, if we want to achieve a plus 40 dB per decade, then we will be using a second order high pass filter, and we can achieve that second order simply by connecting two RC networks with our operational amplifier. Let me draw them for you. So we again have a negative terminal, positive terminal, but this time we will be having one capacitor over there, a second capacitor over there, and then there is a resistor. This is a C1, C2, that is the R2 for the second one, and then there is our R1, and at this point we are applying our input signal, and that is the V output. So that is our second order high pass active filter, and for that particular thing we will be getting a slope of 40 dB per decade. So that is our second order high pass active filter. So now there is another type, and that one is the band pass filter that we just covered very briefly in our previous lecture. So that is actually band pass, that is actually allowing only a specific bandwidth of the frequencies to pass through it, and we can achieve it. One of the ways for achieving a band pass filter is by cascading a high pass active filter with a low pass active filter. So let's directly move toward the second order. So that can be achieved if we have a high pass filter that we just draw before. So that one is a C1, C2, that one is the R2, and then we have our R1 over here. So we are also applying some signal at the input, and then that is also connected over there. That is the V output. But again, at its output of our first stage, we are again connecting a low pass filter at the second stage. That is what we are achieving. So that one will be the C3, R3, R4 and C4. So that is basically we have cascaded the one that was the second order high pass active filter with a second order low pass active filter. So the frequency response for this particular circuit, so that the first stage what would be happening is, now we will be having a response of something like, that is the frequency gain in dB. That for at the first stage we have a high pass, so that high pass will be first blocking some of the frequencies, and then it will be allowing some of the frequencies to pass through it, and then we have a low pass filter, and then that is the frequency response for this particular one. So that is actually the plus 40 dB, because we have a second order high pass filter at this point, and for that one we will be having first corner frequency, and that one would be the corner frequency for the low pass filter, and then in the middle let's call this one FR. So that will be the frequency response of this band pass filter. So this will be actually allowing only some particular frequencies, a bandwidth of some particular frequencies to pass through it, and it will be blocking the rest of the frequencies. And one of the ways through which we have achieved it by cascading a high pass and the low pass filter. So the order is actually not important. You can put a low pass filter at the first stage and then a high pass filter at the second stage, but in every case our response will be the same. So this, for the FC1 we can calculate it by using our previous formula, that is 1 over 2 pi square root of R1 C1 R2 and C2. And similarly for the low pass active filter, second order is so R3 C3 and R4 and C4, and our FR is actually an average, graphical average of our FC1 and the FC2, that is equal to the square root of FC1 and FC2. So these are the formulas through which we can calculate the bandwidth for our band pass filter. So our FC1 will be actually the corner frequency for the high pass filter, and FC2 will be the corner frequency for our low pass filter. So that was